Greetings. So in the previous class we had just discussed the recycling of iron and steel making scraps, and before that we had discussed the iron and steel making slags, and now we are at the end of this discussion on iron and steel making industry wastes, wherein we will be discussing wastewater recycling. Now, why exactly is water being described in a steel making waste club? So, the idea is that in this collection of wastes that we look at from basically iron and steel making industries, water waste is very much prominent. It doesn't appear to be prominent unless until we look at the total quantity of water that is used. So in today's class we will be discussing about how wastewater is generated, in what fronts, and what are the variations in chemical compositions, and what we can do to recycle this wastewater to make it fit enough to reuse, either reuse in the industry itself, or if at all it has to be discharged into the water stream, what is the chemical composition treatment that one needs to do before it is released into the environment. Because we know that the different types of metallurgical wastes that we have seen, let's say from aluminum industries, copper industries, zinc industries, and even in iron industries, we know that the direct discharge of these wastes is hazardous, but most of these wastes were solid, and let's say zinc dust is basically is also actually a solid, but it can be released in the atmosphere also. But most of these wastes are solid. What happens if a liquid is discharged, and if this liquid is discharged directly into the water source? Now we are talking of wastewater that is generated in iron and steel making industry in various units, and the composition of wastewater can change depending on where it was basically generated, and one has to think very judiciously as to what is the process that one has to follow to recycle these wastewater streams. So we'll just begin. Wide range of processes generate wastewater streams. This is not just one single stream, these are wastewater streams. Now let us just broadly see. One might not consider, but mining wastewater is also, one might call it mining drains. So mining wastewater, there is coking plant wastewater that is happening in the metallurgical coke generating unit. Then we have sintering unit. So we have sintering wastewater. And of course these are just pre-treatment units. Finally we are reaching the iron making wastewater. After iron making we'll have steel making wastewater. Then we have steel rolling, because rolling consumes lots of wastewater. Rolling process consumes lots of water, so it generates. And then we have basically the cold rolling process itself consumes water, and that water can contain large amount of metal ions which can be brought back into the material cycle. So we see that these are the categories, broad categories of wastewater that is basically generated in different processes. We know that such is the consumption. What exactly is the overall consumption per ton of steel? So let us look at that. It has been found that nearly 28.6 meter cube water is used for 1 ton of steel production, which means this is the estimate of wastewater generation per ton. Just multiplying it to, let's say, the world production of steel in a given year would give us the water that is used directly in steel making industries, taking into account the totality of the steel making industries of the world. Now, this is what we are really looking at, and this itself is a very large quantity. Of course, this number isn't big when we are just considering 1 ton, but consider the complete steel production throughout the world. Then this number becomes very much significant, and which is itself a big motivation why really it is a big problem, and why really discharging this wastewater into let's say a nearby river or any other water source is definitely not a good option. So quantity of steel versus quantity of water used is basically what we know, and we know that nearly 90% of the water that is used is basically it can get reused by after pre-treatment and removal of ions, because at times we also have to consider some evaporation loss. So even if we consider a given quantity of water is used and we have some losses in evaporation, still the water can be recycled. So that releasing of water is definitely not an option, at least untreated water. So one has to think of treatment so that we can reuse it, or else it can be safely discharged only if we are not intending to reuse it. So that is how we can proceed. Now we must note that what are really the variations in chemical compositions. We've seen the categories of wastewaters, and such a classification of wastewater and the chemical compositions that we are now about to study, the variations are enormous because these are generated in different sources. So one really cannot club these wastewaters together. These wastewaters should be, ideally these wastewaters should be separately treated. We know that it may not be possible, but the chemical compositions vary a lot. So we will now discuss the chemical composition. And here we have table 1, table 2 and table 3 collected from different sources. These are of course from different categories of steel making wastewater. So we have steel making unit, we have cold rolling, and again we have steel making. And with this we can take an estimate that really the chemical composition fluctuates a lot from sample to sample, from unit to unit, and of course from plant to plant. So if in a steel making wastewater sample we can say we have iron 4.8 milligrams per liter. We can also have different other elements. These are heavy metals. So we have As, Cd, Cu, Cr, Hg, Ni, Pb and Zn. Of course these are present in relatively very less quantities. Of course mercury is also in micrograms per liter. That is the scale for mercury in this specific data. So if we look at similarly, if we look at cold rolling wastewater, we see that this data is milligrams per liter, and these are the concentration in ions of ions. We see that here we have sulfates and chloride described here, and we have the metal ions on the side. So we have sodium, calcium, magnesium, iron, and we see that sodium is present in very large quantities in cold rolling wastewater. So cold rolling wastewater is having sodium, sulfate, chlorine, calcium, magnesium and iron. And of course here we see that iron is very less. Again, from a different steel making wastewater stream, we see that the concentration of iron, Fe2 plus, Pb2 plus, Zn2 plus and Cr6 plus, basically hexavalent of chromium. These are present in such quantities. Again the concentration is given in milligrams per liter, and we see that such 309 milligrams per liter is the concentration of iron. So we see that the concentration of various metal ions can fluctuate by a large margin. So at times we can have, let's say, a single digit concentration, and at times it can go to hundreds. This depends on what is the source of wastewater. So simply identifying that okay, we'll recycle this type of wastewater is not going to help. One has to precisely monitor what is the concentration of metal ions in what source. If water sources vary, or let us imagine a situation where different water streams are merged, then keeping a track of concentration becomes very difficult, because then the homogenization of ions may or may not take place, and then one has to build a special reaction mechanism where most of the metals can be isolated. Now that may also become fruitful if we have such technologies developed, but if we have separated sorted streams of wastewater and dedicated units, then we can recycle these wastewater appropriately. Now application of technology, the recycling technology for wastewater, and the technologies that we are about to discuss, let's say reverse osmosis or ion exchange resin beds or nanofiltration units, if these technologies are available, then these can be clubbed one after the other and wastewater in general can be processed. But such facilities have to be developed so that efficient removal of these heavy metals from the waste streams is achieved. So from this table what we see is that in most of the wastewater samples we have iron and we have other heavy metals like chromium, zinc, and in some cases copper and lead, magnesium, sodium. These are present. So one can devise a strategy of precipitating or removing these metal ions, and then if at all these salts can be separated out, further pH balance can be done so that these can be reused in the plant itself. So one has to think of wide range of chemical composition. Wide range of chemical composition for available for chemical composition dictates the recycling process. So if we know that the wide range is available, we just directly focus on the available chemical composition and then directly just work around the given wastewater samples. Now, what are the recycling strategies? Recycling processes. We know that the chemical composition has to be the key because we have a wide range of waste waters. And why do we really need to recycle? Why recycle wastewater? So we know that the quantity is enormous. Just need to multiply the numbers here. So x meter cubed, so in this case it is 28 meters cubed into the total steel. So that is how we could just say that it is actually enormous. And then we know that chemical composition has heavy metals, and it's not safe to discharge, so environmental concern. If that was an engineering concern, this is an environmental concern, and it is very hazardous. Hazardous waste. Now, how do we really go about the recycling process itself? So, conventional processes are basically the precipitation, chemical precipitation. So if we are using sodium carbonate or calcium carbonate, that is basically the chemical precipitation, so that we are able to precipitate some salts. So what we might get is some salts, or we can have chemical reactions. If we are targeting some specific product from wastewaters, then we can have chemical reactions. This can also be aiming removal of these heavy metal ions. So why we are recycling? Because we want to bring it out. So removal of heavy metals as compounds, products. So this can be done. Conventional processes involve the precipitation, or we can also have some sort of oxidation or reduction reaction that can help us in removal of these products. Now, at times these might work, but now the chemical variation itself in wastewater is enormous, one has to think of devising other strategies also on top of them. So when we will now look at those strategies which are beyond the regular precipitation strategy. So one can think of use of ion exchange or reverse osmosis, but we will have this different strategy wherein, let's say, we have feed, we have membrane, nanofiltration membrane, and this gives us permeate. Rejected stream of wastewater. So nanofiltration membrane is generating two types of feeds. So after filtration, the reject of the nanofiltration membrane unit is basically released. That is being processed with organic solvents. So mixing tank is present here, and this mixing tank is basically picking up reject of wastewater stream coming from NF membrane, and this is basically organic solvents. Organic solvents that can be miscible with water. This leads to generation of solution of water and organic solvents, and we have a settling tank. So we had a mixing tank, now we had a settling tank, and after that we have the removal of salts. So here, after the mixing of organic solvents, we let it move to the settling tank where there is the ejection of salts, and we also have the movement of solution to a vacuum filtration. Followed by a distillation unit. And condenser unit. This is basically the filtered solution. And after condenser, what we get is basically treated water. And one stream is actually going up to the organic solvents. So basically this is the organic solvent stream that is recycled here in the condenser. What we see here is that we have a wide variety of products actually. So what are important products here? First step is basically permeate of NF membrane, nanofiltration membrane. The second one is basically the salts that is generated in the settling tank. The third one is the organic solvents. So these are basically cycled, and the treated water, which is what we really wanted. So such type of operations this is just one method by which we can club different types of operations one after the other and remove salts, but it is lot of investment to even think of such recycling strategy. One has to be very sure about what we really wish to remove and to what extent, because we know that most of these processes have their own advantages and disadvantages and their limitations as to what is the limit of metal extraction. Now, if we are able to achieve the desired chemical composition after these processes, then it is acceptable. Else, one really is in a dilemma. What type of processes should be used to achieve the chemical composition? Now, what are the other processes used for wastewater recycling? Here we are just going to jot down some of the processes that people have explored in wastewater recycling and what are the key points that they wish to put up for addressing the wastewater issue. So some of the processes are electrochemical reactions. Electrochemical reactions, that is oxidation. We can have chemical oxidation. We have photo degradation with H2O2 addition, and this is basically H2O2 addition, and UV radiation. We have electrocoagulation. Similarly, we have precipitation. Now, we know that precipitation is a conventional route, but still people have tried different methods. Precipitation of specific products, let's say hydroxides and sulfides. Now, adsorption of various products of, let's say, various heavy metal ions has been explored using many different materials. So we'll just write adsorptions using rice husk or kaolinite, clay, or coke breeze, or nickel aluminium LDH, layered double hydroxide actually, LDH, NiAl LDH, and so on and so forth. So lot many adsorption reagents materials have been used for the adsorption reactions, wherein people have tried to use materials as adsorbents, and the heavy metal ions or the material of their choice are adsorbed, in turn leading to the wastewater recycling. And of course there is the use of microalgae. So one of the microalgae could be Arthrospira maxima, A maxima, and such microalgae have been used for the remediation of wastewater. Now, the degree of success for various types of processes are varied, and this again depends upon sample to sample processing conditions to from one type of process to the other, and what exactly was the chemical composition. Such data is available, and one can really devise an ideal strategy for wastewater recycling if we are able to club these strategies one after the other. But again, it depends upon the economic and technological constraints that are present in the industry. So now we are at the end of this metallurgical waste unit of iron and steel making, and now in the upcoming classes we will be focusing on electronic wastes, wherein we will be discussing different types of electronic wastes and the general methods of recycling such wastes. Thank you.